Well, hello there, Cape Chemistry Unit 1 students. Welcome back to another video. And today we will be helping you prepare for your paper 1 exam. And so to do that, we'll be working through the specimen paper that CXE provided us with. And this is from the year 2017, okay? You know the drill as usual. There will be 45 items on the paper, and you have an hour and 30 minutes to complete those items. So that gives you roughly 2 minutes per question, okay? So we're gonna get into it now with our very first question, which says that when a group 1 metal atom, Q, forms ion Q+, is it true that the positive charge on the nucleus increases? The positive charge on the nucleus increases? That's not true, right? Is it true that the number of protons increase? That's not true. The number of protons stays the same. What happens is an electron is lost, right? So number of protons doesn't increase. Is it true that the number of occupied shells decrease by 1, right? Is that true? Let's look at this one a little bit more closely, right? So if we have, say, sodium, for example, right? When sodium forms a Q+ ion or Na+ ion, right? But in its neutral state, it has a configuration of 281, right? So there are 2 electrons on the innermost shell. There are 8 electrons on the second shell, and then the final shell has only 1 electron, right? So if sodium loses 1 electron, right, then it's going to end up losing that whole shell, right? And sodium is in group 1. So we're talking about group 1 metals here. And they all have what? 1 valence electron. So they all have 1 electron in their outermost shell. If they lose that 1 electron, they lose the whole shell, right? And so instead of now having 3 occupied shells, they'll only have 2. So the number of occupied shells does decrease by 1. So this is correct, okay? So our answer for 1 is C. So the key things to note here is which group are we talking about? We're talking about group 1, where they have 1 in their outermost shell. And if they lose that 1 to form a Q+ ion, they're going to lose that whole shell and just end up with only 2 as opposed to the 3 in the case of sodium, for example, right? So it has the number of occupied shells decreases by 1. Would the radius of the particle increase? No, because it's losing a shell, right? So the radius would actually decrease, right? So this is not true either. So our only true thing here is C, okay? Okay, so moving along to 2. 2 says radioactivity is hazardous because, is it because it can cause cancer and sterilization in human beings? Not really, that's not why we say it's hazardous. So that's not correct. Is it because radioactivity is hazardous? Is it because it is accumulative and interacts with matter? Not particularly. Is it because it needs to be transported and properly disposed of? That's not why it's hazardous. It's because it's hazardous why we need to do this, right? But why is it hazardous? It's because it has particulate as well as high energy emissions, right? So that's going to pose a hazard for us, right? So the answer for 2 is D. If something has particles that it can give off, which radioisotopes or things that are radioactive do, and they also have these high energy emissions, like you have your gamma rays, right? That comes out of a radioactive decay. That's a high energy emission, and that's hazardous for us, okay? So it's because radioactive particles have these particulates as well as high energy emissions that causes them to be hazardous, right? All right. So moving along to 3 now. 3 says, in which of the following compounds will hydrogen bonding not be present? Right? So we have to think back to how did we define hydrogen bonding? Hydrogen bonding refers to when hydrogen is covalently bonded to either a fluorine atom, an oxygen atom, or a nitrogen atom, or the hydrogen is bonded to a compound that has these atoms in it having lone pairs on them, okay? So let's look at the list here. C2H5I, we don't see any of these very electronegative atoms here. So this right away, we can rule this out. There won't be any hydrogen bonding here, right? So our answer for 3 is A. If we look at this alcohol, we know that alcohols they have this OH, so that's hydrogen bonding right there. We have NH2 here, N and H are going to be bonded to each other, so that's going to have hydrogen bonding. And then in the sulfurous acid, we have hydrogen bonded to oxygen, right? That's the structure of sulfurous acid. So again, we'll have hydrogen bonding here, but in this case, we won't because it doesn't have any of these highly electronegative atoms on it, okay? So our answer for 3 is A. No hydrogen bonding will be in A, okay? All right. So moving right along to question 4. Question 4 says, which of the following species has a structure with a bond angle less than 109 degrees, right? So remember, 109 degrees would be a tetrahedral angle, right? So we can't choose anything that has a tetrahedral shape. We need something that's less than a tetrahedral or less than 109, right? So the possibilities are that it could be a trigonal planar molecule, which has bond angle of 107 degrees. It could be an octahedral molecule that we choose that has a bond angle of 90. Or it could be a bent or V-shaped molecule that has a bond angle of 104. All of these would be less than 109, right? So we can choose a tetrahedral structure. So first of all, let's look among our answers for the tetrahedral ones and just strike them out, right? So we know that this would be methane is a tetrahedral molecule, so we can choose that. That's going to have bond angles of 109. NH4, so that ammonium ion is also tetrahedral, so we're going to have to strike that out, right? Now, we have to choose between these two, A and D now. That's what's left, right? So let's look at the structure over here for NF3, right? So nitrogen, we know, has what? 5 valence electrons, right? So it has 5 electrons that it can contribute to bonding. Now, if it bonds with fluorine, which only needs 1, right? Because fluorine is what? 2, what's fluorine? Fluorine is 9, right? So it would be 2, 7. So it only needs 1 to be satisfied. And so we can have 1 of the electrons from nitrogen bonding with it, 1 bonding with this and 1 bonding with this. So it uses up 3. And so we have 2 remaining. So we have a lone pair here, and we have 3 bonded pairs here. Right? And when we have 3 bonded pairs and a lone pair, that's going to form a trigonal pyramidal structure with bond angle 107. So our answer for 4 will be A, because right away, we see that we have this 107 that's less than 109. If we look at BF3 now, that's boron, right? And boron has an atomic number of 5. So there are only 3 electrons that it can contribute to bonding. So there's literally only going to be 3 bonded pairs, right? When we have 3 bonded pairs around a central atom, we're going to get a trigonal planar structure, and that has bond angles of 120. So still, that's not less than 109. The only thing that's less than 109 is the NF3, and that has a bond angle of 107 because that's trigonal pyramidal by virtue of these lone pairs here, okay? All right, so our answer for 4 then is A. All right, so moving along now to question 5. Question 5 says the molar volume of a gas at room temperature and pressure, so RTP, is 24 dm cubed. If 0.032 grams of a gas occupies 48 centimeter cube at RTP, what is the molar mass? Okay, so we need to find the molar mass, which is the grams that are present in a mole, right? So this is my G, grams that are present in a mole. All right, so we know that the molar volume of a gas is the volume of 1 mole of the gas, okay? So at RTP, we know that the molar volume, 1 mole is gonna occupy 24 dm cubed, right? And we know that this actual gas occupied 48 cm cubed. So let's find out how much that is in dm cubed. That would be 48 divided by 1000 dm cubed. So that's how much space this gas occupied at RTP, right? So if we know that 1 mole of a gas occupied 24 dm cubed, and they're telling us that, but actually this gas occupied 48 divided by 1000 dm cubed, then how many moles must that have been, right? So let's follow the calculation through here. So this actually ended up being 0.048 dm cubed, right? And we know that 1 mole took up 24 dm cubed. So all we're gonna do is divide this volume by the volume that 1 mole would have taken up to find out how many moles do we actually have, right? So we have, it turns out that we have 0.002 moles of this gas present. And that 0.02 moles is equivalent to 0.032 grams, because they told us that that's however much, that's what that amount of gas weighs, right? That occupies this amount of space. It weighs 0.032 grams. So we know that that 0.02 moles that we calculated is actually corresponding to that 0.032 grams, right? So now, if we know that that 0.002 moles corresponds to 0.032 grams, then how many moles is that, right? How many, what would be the mass of 1 mole? Because we need to find the molar mass, right? So if 0.002 moles weighs this much, then 1 mole will weigh, so we're gonna multiply this number, right? We're gonna multiply that number by 500, right? To make it 1, right? So 1, let's see. So multiply that number by 500 to make it 1. So we calculate this through again. So we multiply that number, 500 times 0.002 to make it 1. So I multiply this by 500, and so we have to do the same for this one to get to how much 1 mole would weigh, right? And when we do that, we come out with wait a minute. Let's see, 0.032 times 500, we come out with 16 grams, right? So our molar mass is 16 grams. So just to recap, how we ended up here, we know that 1 mole of a gas occupies 24 dm cubed. And so if they're telling us that this particular gas occupied 48 cm cubed at RTP, then we can find out how many moles of the gas was present. And it turns out that that was 0.002 moles, right? And they also told us how much this volume of gas weighs, and they said that that was 0.032 grams, right? So immediately we know how much 0.002 moles weigh, and that's 0.032. So then if we want to find out how much 1 mole would weigh, which is the molar mass, we just scale up, right? Multiply by 500, we get to 1. Multiply this side by 500, we get 16 grams. So the molar mass is 16 grams, right? And so that's our answer for 5. 5 is C. So moving right along to 6. 6 says that propane is a fuel used in lamps. The equation for the combustion of propane is that we have 1 mole of propane reacting with 5 moles of oxygen to then form 3 moles of carbon dioxide and 4 moles of water, right? So the question is saying what volume of CO2 is produced when 8.8 grams of propane is burnt in oxygen at RTP. So we're at RTP, and we know that at RTP, 1 mole of a gas is gonna occupy 24 dm cubed, right? So let's just write that down right away. We are at RTP. So 1 mole of a gas will take up 24 dm cubed, and they want us to find what's the volume of carbon dioxide if 8.8 grams of propane is burnt in oxygen, right? So right away, we look at this balance equation to see what our mole ratios are, right? How do we relate propane to carbon dioxide? For every mole of propane that we burn, we're gonna get 3 moles of carbon dioxide, okay? So that's important right from the jump. It's a 1 to 3 mole ratio. So what we have to do, guys, first of all, then is find out how many moles of propane do we have, right? We know that 1 mole is gonna get us 3 moles of CO2, right? So how many moles of it do we have? And then by extension, how many moles of carbon dioxide will we get? So what we have to do then is convert this 8.8 grams to moles. And so we do 8.8 grams divided by the molar mass of let's see, molar mass of propane. Yeah, so we will actually, let us do it this way. Let's do it this way. So 3 times 12 plus 8. 3 times 12. Okay, yeah. So the molar mass of propane is 44. So if we do the mass of propane divided by the molar mass of propane, then we get how many moles of propane were present, right? And so that's 0.02 moles of propane. And so that 0.02 moles of propane now, we would have known right from the jump that then we would also get how many moles of carbon dioxide. We know that we'd get 0.6 moles of carbon dioxide, right? But the question is not asking us about moles, it's asking us about volume, right? So this is how we approach it. We use Avogadro's law, which says that equal volume of gases under the same condition of temperature and pressure will occupy, will contain the same number of molecules, right? And so 0.2 moles is gonna occupy what? 24 dm cube over 5 dm cube, because 1 mole, remember now, 1 mole would occupy 24 dm cube. So a fifth of that, right, which is 0.2, would occupy 24 divided by 5, right? So a fifth of it is what we have in propane. So that's 4.8 dm cube, right? So propane, this 8.8 grams of propane actually occupies 4.8 dm cube. Now, because it's in a molar ratio of 1 to 3 with carbon dioxide, then the amount of carbon dioxide that's present will be 3 times this amount, and that's per Avogadro's law. And so we'll end up with 14.4 dm cubed. And so our answer for 6 then is C, right? So we see that that's C here. So just to recap, we look at our mole ratios first and foremost. So it's a 1 to 3 for propane to carbon dioxide. We convert our mass of propane that they give us to moles, right? And once we get the number of moles, then we can find out how much volume that would take up. And so we got that to be 4.8 dm cube here. And using Avogadro's law, we can just say that, okay, if the molar ratio is 1 to 3, and I have 4.8 dm cube of this, it means that I'll get 3 times that 4.8 over here. And that turns out to be 14.4 dm cube. So our answer for 6 is C. Okay? All right, so moving along to question 7 now. Question 7 says, which of the following are redox reactions? So that's an oxidation reduction reaction. So that means that there's some change in oxidation state of all of our species happening, right? All of them, their oxidation numbers have to change. So let's look at these equations that they gave us, or these reactions. So let's look at the first one. We see that we have hydrogen peroxide here. And in hydrogen peroxide, we know that oxygen has an oxidation state of -1, and there are 2 of them. So that means that hydrogen has an oxidation number of +1, right? Over here, we see that it's the same, it's +1 still, and then the oxygen, we only have 1 here, and that changes to -2. And then we see that the oxygen ends up also being reduced to 0, right? So, well, oxidized to 0 in this case. So we're going from -1 to 0, that's an oxidation. So let's just follow that. That's an oxidation, right? That's oxidation, right? And it's also being reduced. So this is a disproportionation reaction, but it's also a redox reaction, right? So this is going from -1 to -2. So that's a reduction. So that's a redox reaction. So 1 is good, right? 1 passes the test for a redox. Let's look at the second one. We have iron going from 3+ to iron in 0. So that's a reduction, right? And then we have oxygen going from -2 to -2. So that one didn't really change here. And then we have aluminum going from 0 to +3. So that got oxidized, right? So the aluminum got oxidized and the iron got reduced. So this is redox, right? Let's look at this last one now. We have barium chloride, where barium is in +2, Over here, barium is still in +2. So nothing happened to barium. Let's look at chlorine. Chlorine was -1 in barium chloride. It was still -1 in hydrochloric acid. So that didn't change. Hydrogen was +1 here, and it still is +1 over here. Sulfur is +6 here, it still is +6 here, and oxygen is -2 here, and it still is -2 here. So no change occur here, no reduction, no oxidation, and so this one doesn't pass that test, okay? So in the end, we get that 1 and 2 are redox reactions, and so our answer is A, right? A matches that. 1 and 2 only. 3 doesn't count as a redox, okay? So 7 is A. And we're moving along to 8. 8 says in the reaction between potassium manganate 7 and potassium iodide in acid solution, the following relevant half equations can be written, right? So we have 2 moles of our iodide ion going to the neutral iodine molecule plus 2 electrons. And then we have MnO4, so that's our manganate 7, plus H plus 5E going to our manganate 2 plus, right? So that's a reduction plus 4H2O, right? And in this case, it was an oxidation because we're going from -1 to 0, right? All right, so it's a redox reaction that we're looking at here. Now they're saying which of the following is the overall balanced equation, right? If they give us these half equations and we want to find the overall balanced equation, we have to multiply, we have to make the number of electrons or the charges in both equations, in both half equations, we balance, okay? So in this case, I multiply by 5, the top one by 5, and I multiply the bottom one by 2. So that way, when I come over here, I'll end up with 10 moles of iodide ions goes to 5 moles of I2 plus 10 electrons. And then when I come at the bottom now, I have my 2 moles of manganate 7 plus 16H plus 10 electrons goes to 2 moles of Mn2 plus 8 moles of water, okay? And so you see here that the 10 electrons up here can cancel the 10 down here, right? And that was the whole point of us multiplying by these numbers. And when we do that now, and we cancel our 10 moles of electrons, our overall balance equation ends up being 10 moles of iodide ion plus 2 moles of MnO4 minus plus 16H plus is going to give us 5 moles of iodine molecule plus 2 moles of Mn2 plus 8 moles of water, plus 8 moles of water. So we're going to look for that answer among these. So we're looking for 10 iodide. So that's this one. 2 MnO4, 16H plus, 2 Mn2 plus, 5 iodide, and 8 water. So that's C, right? So the key thing here is just to make sure that you balance your charges from the jump and then cancel out whatever cancels and you come up with your overall balanced equation, okay? So 8 is C. So moving along to 9. 9 says, which of the following is not true about a dynamic equilibrium? Okay? Is it true that dynamic equilibrium is reversible? That's true. We normally show them as these reversible arrows, so it's reversible. Are the macroscopic properties constant? So what we see, yeah, we're not really seeing any changes in terms of like the large bulk properties that we see, right? So we normally say the concentration is constant. So macroscopic properties are constant. That's true. Are the microscopic processes in balance? Yes, that's true, because you constantly have, you know, the reactants converting into products and products converting back into reactants. So the microscopic processes are in balance. Is it true that dynamic equilibrium cannot be achieved in a closed system? That's false, right? You need to have a closed system to have dynamic equilibrium. So the fact that they're saying it cannot be achieved in a closed system, that's wrong. That's not true, okay? And they asked us what's not true, and it's this one that's not true. So our answer here is D, right? We need closed systems for dynamic equilibrium. So if you're telling us that we can't be achieving a closed system, that's not true, okay? All right, so moving right along to 10. 10 says that the volume of nitrogen gas collected at RTP when 0.01 mole of ethyl amine completely reacts with an excess of nitrous acid is, so this is our balance equation that we're using now. We want to find the relationship between nitrogen gas and ethyl amine. So this is our ethylamine, and we see that we have 1 mole of it in the balance reaction. And we see that this is our nitrogen, and we have 1 mole of it, right? So the mole ratio is 1 to 1, right? So based on that, if we have 0.01 mole of ethylamine reacting with the nitrous acid, then that means that we're going to get that same amount of 0.01 mole of nitrogen, right? Because they're 1 to 1. No, we are at RTP, so that 1 mole of that ethylamine or 1 mole of that nitrogen would have occupied 24 dm cubed. But we don't have 1 mole of it because it's only 0.01 mole of ethylamine that we started with. So we only have 0.01 mole of nitrogen gas, and that 0.01 mole will only occupy 24 divided by 100, right? Because that's the scale 1 to 0.01, and then that would be going to 0.24 dm cubed, right? So 1 mole occupies 24 dm cubed, but we only have 0.01 moles, so that will occupy 0.24 dm cubed. It's just a ratio here, right? And so our answer is then B, okay? So that's 0.24 dm cubed. That's the volume of nitrogen gas that would be collected, okay? All right, so 10 is B. Moving along to 11. 11 says that a mass of 25 grams of an unknown gas X is pumped through an industrial pipeline of volume 60 centimeter cube at a pressure of 120 kilopascal and temperature of 150 degrees C. And they're giving us the molar gas constant as 8.31 joules per Kelvin per mole. Right, so when you see this kind of problem now, and they're asking you to find the relative molecular mass of the gas, that's big M, right? When they're asking you to find that, you know right away you're gonna have to use your ideal gas equation, which says that PV is equal to nRT, right? So PV is equal to nRT, and N is the number of moles, right? We know that the number of moles is gonna be the mass of your gas divided by the molar or the molecular mass of your gas, right? So if we want to find the molecular mass, then we're going to rearrange it as such so that the molecular mass will be equal to the mass divided by the number of moles, right? So let's plug in this equation here. We rearrange to make moles the subject so we can get the molecular mass or MR in it. And so over here now, I've plugged in the values that we know. So this is our pressure times volume. So we have to make sure that everything is in SI unit first of all, right? So this is our pressure. They told us it's 120 kilopascal. So I just multiplied by 10 to the 3 to get it just to be in Pascal. They told us that our volume is 60 centimeter cube. We need that to be in meters cube. And so we're going to divide this by 1,000,000. So I did 60 times 10 to the negative 6 for my volume. And then my R term now is here, 8.31. And then my temperature is here. I have to convert the Celsius to Kelvin so that I just add 273 to that 150, right? And then what I came out with now, once I multiplied through the top and then divide by the bottom, I get 7.2 divided by 3,515.13. And I come out with 2.048 times 10 to the negative 3 moles, right? So that's the number of moles of the gas that we have. And so remember we said over here that the number of moles is equal to your given mass divided by your molar mass. So now we're ready to find our molar mass or molecular mass, right? So we just rearrange to make MR the subject or molecular mass the subject. So then the molecular mass then is going to end up being the given mass divided by the number of moles, right? Now, the mass that we need to use here is the Kelvin, since that's what's coming out of this SI unit-based equation. So we do 2.5 grams to the 25 grams. We're going to convert this given mass to kilogram. And so we do 25 times 10 to the negative 3 kilogram. And then we divide it by the number of moles, which we got from here, which is 2.048 times 10 to the negative 3 moles. And we come out with 12.2. So our answer for the relative molecular mass of the gas is D, okay? So our answer for 11 is D. The key is just remembering that we can apply the ideal gas law and we can rearrange that to solve for molecular mass. And that's exactly what we did here to end up with 12.2, which is D, okay? So 11 is D. And so moving along to 12, 12 says that the melting points and boiling points of two pure substances, X and Y, are given below. So here's our X. X has a melting point of 273. This is the temperature at which it goes from a solid to a liquid. And then the boiling point is 373. So this is the temperature where it would go from a liquid to a vapor, right? So for Y now, the melting point is 317, and then the boiling point is 400, and that's all in Kelvin, right? So which of the following statements about X and Y are correct? Is it that at 298 Kelvin, the particles of X can occupy the volume of its container? Well, let's think about this. At 298 Kelvin, right? So if we have 298 Kelvin, that means that we've melted the solid, right? And we're in a liquid phase, right? So at 298, X is a liquid, right? And then the boiling point is 373. So it wouldn't be a vapor, it would be a liquid, right? So at 298, it's a liquid. So do liquids occupy the volume of its container? That's not true, right? So that's not a true statement. It's gases that can fill the volume of its container. But this is not a gas at that temperature. It's a liquid, right? We've literally just melted it, so it's a liquid, right? So at 298 now, is it true that the particles of Y are fixed in position? So if we're at 298, what are we? What state are we going to be in? We're not melted, right? So we're still in a solid phase. That's Y, right? So Y would still be a solid at 298 because it melts at 317. So it's still a solid at 298. And so the particles of Y would be in fixed positions, right? Remember that solids are fixed and they just vibrate about a fixed point. So they're fixed. And so this is correct, right? So this is correct about Y at 298. And then at 380 now, is it true that the particles of X would have more energy than the particles of Y? So let's look at it. At 380, right? At 380, what do we have? We have vapor because we're above the melting point. We're above the boiling point and the melting point. We're in a vapor phase, right? So X will be in a vapor phase because we have a temperature that's above its boiling point. So we'll have vapor, right? And we know that vapor can move a lot faster than whatever we would have in Y. If we're at 380, right, we don't have vapor for Y. We're still in that liquid phase, right? Because we're above the melting point of Y, so we would have liquid, but we're not above the boiling point, so we wouldn't have vapor. We would have liquid down here for Y, right? And so we know that vapor are more, the particles are more energetic and they have more energy. And so the particles of X then, right, would have more energy than the particles of Y. And so this is a correct statement. So which of the following statements are correct? One is not correct. So it's just going to be 2 and 3, okay? So 2 and 3 is C. So our answer for 12 then is C, okay? So this is just testing your knowledge of states of matter, and do you know what the definitions are for the melting point and the boiling point, okay? So the answer here is C for 12, and we are moving along to 13 now. So 13, so this says item 13 and 14 refer to the following options. A would be applicable for the enthalpy of formation, B for the lattice energy, C for enthalpy of solution, and D for enthalpy of hydration, okay? So it's important that we know immediately what these definitions are in our head, so we'll know when we can apply them, okay? So let's look at 13. 13 says that if we have a solid Y that's combined with a gas, oxygen gas, to form this oxide, this gaseous oxide of Y, what do we call this? Would this be an enthalpy of formation, lattice energy, enthalpy of solution, or enthalpy of hydration? It turns out that this is the enthalpy of formation, right? Because we have 1 mole of a substance that's being formed from its elements in their native state, right? So we have a solid and we have a gas coming together to form this molecule. Using these from these elemental forms, right? And so this is a enthalpy of formation for this oxide. So our answer for 13 then would be A, okay? So our answer for 13 is A. Again, we're just remembering the definition so we can apply them here, okay? So if I have for 14, what I have is a solid compound. Maybe this is like an ionic compound, right? That's in a solid state, XY. And I am dumping this in a bunch of water, right? To then form XY in its aqueous state. Now, when I do this kind of a thing where I have a solid that's being dumped in water, right? What we have is a solution that's being formed in this particular case. That's the enthalpy of solution, right? That's what it's defined as. And so the 14 would represent an enthalpy of solution. So 14 is C, okay? All right, I'm basically just forming a solution from this solid. So that's an enthalpy of solution, okay? So 13 is A, 14 is C. So moving along to 15 now. 15 refers to the diagram below, which shows a Born-Haber cycle for sodium chloride, okay? So let's look at the Born-Haber cycle. It's important that we remember what each steps are, right? This would be the enthalpy of formation, right? So that would be delta HF. And over here would be our lattice energy or lattice enthalpy, where we're combining these gaseous ions to form the solid, the ionic solid there. And of course, you know, these steps here, we have our atomization of sodium, we have atomization of chlorine, then we have the first ionization of sodium, and then we have the electron affinity, the first electron affinity of chlorine, where we're pushing on an electron onto it, right? And so let's see, they're asking us what is the lattice energy of sodium chloride? So they want us to find this one, what this number here representing this step should be, okay? So that's my delta H lat for sodium chloride. And so there are several ways to look at it, but I found the easiest way to be, think of this as picking one direction that you're moving into, right? So let's pick this direction and we're going from here, right? And we're coming around in a clockwise direction. So what I'm going to do is I'm going to add up all of these. Of course, we're observing their sign and keeping their sign. So I'm going to add up all of these from here, coming all the way around to here. And I'm going to come back to my starting point. And when I do that, so when I go around and I add up everything and I come back to my starting point, the sum should be 0, right? Because I've literally looped around and come back to where I've started. But in that, this is my unknown delta H lat. I don't know it, right? So here's how we're going to do it. It would be 107, right? 107 plus 122 plus 436 plus minus 349. So that's what I have here. Plus my delta H lat. Plus, this is going to change sign because it's going, we're going against this arrow, right? So this would then become plus 411. So here I do plus 411 and all of that must add up to 0, right? Because I've done a whole loop, come back to where I start. So that should end up being equal to 0. So that way now, all of these numbers, when I add up this and this, I get 727. So my delta H theta lat plus 727 should give me 0. Now I want to rearrange to solve for my delta H lat. So delta H lat is just going to be equal to, we're moving this to the next side, right? So we're going to get negative 727 kilojoules per mole for our lattice energy of sodium chloride. So let's look for that in our answers. And we see that that's A, that's the very first one. Okay? So that's the easiest way to kind of really break down these Born-Haber cycles when you're to find an unknown lattice energy. You just pick a direction. I've picked a clockwise direction, and when I sum up every single thing, they should come to 0. Because this arrow is going against my clockwise direction, then I have to make it positive. And so that's what I did here. And I ended up with this number here. And then finally, I just brought this to the other side to get my lattice energy, okay? All right, so that's that. And so 15 was A. And so moving along to 16 now. 16 says that the general form of a rate equation is given by rate is equal to this rate constant times the concentration of A raised to A, little a, and then times the concentration of B raised to little b, okay? So the question is saying now the rate constant K, so this K here is defined as the rate of reaction when the concentration of each reactant in mole per dm cube is it when the concentrations of each reactant are 0? Let's try that. Let's try that. If we had 0 here and 0 here, then this would be 0. That wouldn't be an actual number. All of this would go away and the rate would be 0. The rate wouldn't be K, right? So A is not our answer. Is it when the concentration of each of these is half? If this is half and this is half, we will have a number here times K and not just K, right? So this wouldn't work. But if the concentration of each reactant is 1, right? So if this is 1 and this is 1, then what's going to happen is that we're just going to have rate is equal to K, right? Because 1 times 1 is 1, K times 1 is K. So our rate would be equal to K when these concentrations themselves are 1, right? So that's 1 times 1. So that's C, okay? So we're literally just plugging in these numbers to see which one would have us ending up with rate equal K. And that's when these concentrations are 1 mole per dm cube, okay? So the answer for 16 is then C. And so moving along to 17. 17 says, item 17 refers to the data in the table obtained for the reaction between molecules X and Y at 500 Kelvin, right? The stoichiometric equation for the reaction is 2x grams plus y 2 grams goes to x2 y2 in gas, right? So this is our state symbol gas. So 2 moles of X in the gas phase react with 1 mole of Y2 in the gas phase to go to X2 Y2, 1 mole of X2 Y2 in the gas phase. Okay, so that's this stoichiometric reaction here. Now they're saying now, they're showing us 3 experiments. Experiment number 1, 2, and 3, initial concentrations of each of these species, and then the initial rate that's associated with these concentrations, okay? So they're saying now the correct orders of reaction with respect to X and Y are, so we have to find it, right? So before we even look at what they're giving us to choose, let's look at it. Let's look at the actual table to see if we can come up with the orders of the reaction with respect to the reactants, okay? So to find the order with respect to X, we are going to keep Y constant and change the value of X. And so the experiment 1 and 2 shows when we're changing X. And when we double up X, right, we see that we double up our initial rate. So if I do double and I get a double in response in terms of my rates, then that means that it's first order with respect to the thing that I change. So it's first order with respect to X, okay? Because when I double it, I get a double in the rate. When I double the concentration of X, I get a doubling of my rate, okay? So if I want to find out the order of the reaction with respect to Y, then I'm going to, what am I gonna do? With respect to Y, I'm going to change my Y value. So here I'm changing my Y value. I'm going from 0.02 to 0.01. So I'm halving my concentration of Y, and then I'm keeping my X constant. So actually I'm gonna be using 1 and 3. Right, so I'm keeping X constant, so it's 0.01 here and it's 0.01 here. And then for my Y, I'm going from 0.02 here in experiment 1 to 0.01 here. So I'm halving my Y, and when I halve my Y, I see that my rate goes from 2.42 in experiment 1 to 1.2 times 10 to the negative 6. So that's being halved as well. So if I halve my concentration of Y, I halve the rate of the reaction. So that means that it's a first order as well, right? So the reaction with respect to X and Y is first order. So we're looking for that, and it turns out that that's D here, okay? So with respect to X, my reaction is first order, and with respect to Y, my reaction is first order, okay? So in both cases, the reaction is first order in respect to both reactants, okay? All right, so moving along to 18 now. Item 18 refers to the following data for the reaction between propanone, iodine, and hydrogen ions. So we see that we have our propanone here, we have our H+ ions, we have our iodine, and we end up getting this and these, okay, as our products. So we have a table here that's showing experiment number. There are 4 experiments that they would have done in this case. And then we have our concentration of propanone, H plus, and iodine here. And we have the corresponding rate when the concentrations are these values, okay? So down further, it says that the rate of the reaction is given by rate is equal to this rate constant times the concentration of propanone raised to X times the concentration of H plus raised to Y times the concentration of I2 raised to Z. The values of X, Y, and Z are, so we have to find them, right? So we have to find the order of the reaction with respect to propanone, with respect to H plus, and with respect to I2. So again, we can use our experimental values, and let's start with propanone. So if I want to find what the order of the reaction is with respect to propanone, I'm gonna change propanone and keep everything else constant. So I'm gonna keep my H plus constant, and I'm gonna keep my I2 concentration constant. And it looks like in experiment 1 and 2, that would work, where we keep those 2 constant and we change the propanone, right? So between experiment 1 and 2, we're doubling our concentration of propanone. And when I double my concentration of propanone here, we see that we get a doubling of the rate as well. So that means that the reaction is first order, right? With respect to propanone, and that's that X here. So that X would be 1. Right? It's first order because if I double the concentration of propanone, I double the rate. Okay? So let's look at H plus now. If I want to select two experiments where I am changing my H plus but keeping I2 and propanone constant, I could use experiment 1 and 3, right? So when I look at experiment 1 and 3, let me get back my pencil. Yeah, when I look at experiment 1 and I look at experiment 3 now, I see that my propanone concentration is being held constant, which is what we want to do. And then we're changing the H plus concentration from 0.1 to 0.2. So we're doubling it, right? So I double my H plus concentration and I keep my I2 constant. So when I double my H plus concentration, when I go from experiment 1 to experiment 3, then I also see that there's a doubling of my rate. And so that means that it's first order with respect to H plus, okay? So that Y then would also be 1. Let's look at Z now for iodine, the order of the reaction with respect to iodine. So if I change iodine, I could look at experiments 3 and 4, right? So that would be 3 and 4, right? So of course, I'm keeping propanone constant, I'm keeping H plus constant, and I'm changing iodine. So if I double up iodine now, I'm going from 0.1 to 0.2. I see that my rate doesn't change, right? So when I change the iodine concentrations, in fact, I've doubled it and I don't see any change in the rate, it means that the rate doesn't depend on iodine, right? And if a rate of a reaction doesn't depend on a particular reactant, then it means that it's 0 order with respect to that reactant. And so my values for X, Y, and Z would be 1, 1, 0. So let's look for that, and we see that that's C. Okay? So the answer for 18 here is C. All right? So moving along now to question 19. Question 19, item 19 refers to the graph below, which shows the Boltzmann distribution of kinetic energies in a gas, right? So let's look at that. So we see on the x-axis, we have energy, the energy of the molecule. And then over here, we see that we have number of molecules with a given energy, right? No, they're asking us which of the following statements are correct for the Boltzmann distribution, right? Is it true that when we increase the temperature, we're going to cause the maximum of the curve to shift to the right? So it's going to shift over here. Is that what we're going to see? Are we going to see that there's an increase in the total number of molecules? Or are we going to see that there's an increase in the number of molecules with energy greater than the activation energy? So first of all, let's just rule out the second one. If we increase the temperature, there's no way we can increase the number of molecules because the number of molecules is what it is, So we're not going to be able to change that by just changing the temperature. So we can rule out that. That's not correct, right? Now, let's think about the other ones, right? In relation to the Boltzmann distribution. So for the Boltzmann distribution, when I increase the temperature, my maxima is in fact going to shift to the right? So in that case, I'm going to end up with a curve that looks like this, right? And so what's happening here then is that, so this is my new temperature. So this will be my T2, right? And I started out here. I increased the temperature and my maxima got shifted to the right. So that's correct. It would be shifted to the right. And now remember, if we say, for example, that this is our activation energy, EA, right? In the previous case, so the area under the curve, right? The area under the curve represents the number of molecules having a particular energy, right? So in this case, the area under the curve when I was at T1 was only this that I'm shading here, this shaded region. So only these many particles had the activation energy, right? These ones out here. But when I increase the temperature and the maxima shifted to the right, the area under the curve increased, right? So we had more molecules. I should have used a different color for that. So let's do that. So now we have these molecules, right? In addition to these that we had down here that now have the required activation energy, right? Because remember the area under the curve, which is this, represents the number of molecules having that particular energy, okay? So what's true? It's true that we're going to cause the maximum of the curve to shift to the right. So this shift to the right, and we see T2 here, and then our activation energy, assuming it was somewhere like around here, we're going to have more molecules since the area under the curve increased. We're going to have more molecules having energy greater than the activation energy, okay? So this is correct as well. And so our answer for 19 then will be B. So that's 1 and 3 only, okay? Remember we had said that it's 1 and 3 only. 2 doesn't count because we can't change the number of molecules by just changing the temperature. That's not how it works, right? It's kind of a closed system and we already have X amount of molecules in it. And so by changing the temperature, we're not going to change the number of molecules. But what we can change, what will happen is that we'll change the number of molecules that are already in there with energy that's greater than the activation energy. So what we can change is the energy of the molecules that are already there. And so we can make it so that they have they are able to exceed the activation energy, okay? So the answer for 19 is B. All right. So moving along now to 20. All right. So this is an interesting one. So 20 is based on the Chatelier's principle, right? So based on the Chatelier's principle, which combinations of observations is not true? What's not true, right? So remember what Le Chatelier's principle says. Le Chatelier's principle state that you know, when you impose a change on a system that's at equilibrium, the system will move in such a way that it would counteract that change, okay? So if I'm already at equilibrium and you're imposing a change on me, I'm going to move in such a way to maintain that equilibrium, right? So I'm going to oppose that change, right? So let's look at this now. Look at this table now. Remember, we're looking for the observations that would not be true based on the Chatelier's principle, right? So let's look at this first one. For this first one, we have an endothermic reaction. So if we look at that, then we would have, say, at A plus B, this is a plus, we have A plus B going to, say, C plus D, right? And if it's endothermic, it's going to give off heat. It has a positive delta H. So it would be positive here. It's endothermic. It's going to give off heat. So whenever this reaction proceeds, it's going to give off heat, right? That's what it does. If it goes this way, it gives off heat. So if I drop the temperature on the reactant side, so say I drop the temperature, right? In my equilibrium state, I am forming, right? I'm giving off, well, I'm absorbing heat. Endothermic reactions absorb heat, right? So this is positive, so it absorbs heat when it goes this way, right? So if I decrease the temperature, then a decrease in temperature would mean that I am dropping the heat content of the system. So the reverse reaction is a reaction that gives off heat. So let's write that. So the reverse reaction, so the forward reaction, so I'm going this way, I'm gonna absorb heat, right? Absorb heat in the forward reaction, right? The backward reaction now, so this arrow gives off heat. Gives off heat, right? Remember now, this is the endothermic case. In the exothermic reaction, the forward reaction absorbs heat because that's why it's a positive delta H, and the backward reaction gives off heat. Okay? So, if I decrease the temperature of this system, right, the reaction is going to want to go in a way to compensate for that drop in temperature. It's going to want to shift to the left, right? And so if it shifts to the left, what we'll see is that we'll have more reactants forming, and so we'll see an increase in our reactants when we decrease the temperature, and we'll also see a decrease in our Kc, because remember now, Kc is the concentration of your products at equilibrium, right, over the concentration of your reactants. So if I have more reactants, right, so this is just an inverse relationship between Kc and reactants. So if my Kc would decrease if my concentration of my reactants increase, and that's what's happening if I'm favoring the backward reaction, right? So if I'm favoring the backward reaction, I'm increasing my concentration of reactants and by extension, decreasing my Kc. So A is a correct thing. We would observe this. So this one is correct. We would observe A. So let's look at B now. Endothermic reaction again, just like we have here, but in this case now we're increasing the temperature, right? So let's scratch this off. We're not decreasing temperature anymore. We are increasing the temperature, right? Remember now, this is an endothermic reaction, so the forward reaction absorbs heat energy. So if I'm increasing the temperature of the system that's originally at equilibrium, and I'm increasing the temperature, it's going to want to go in such a way that the equilibrium is going to shift in a direction so it can absorb that heat energy. And remember, we said that the forward reaction is what absorbs heat, so it's going to go towards the right, and so it's going to favor the products, right? So the number of products that we have will increase and the number of reactants will decrease because we're using them up to go to the forward side so we can absorb the heat that we put in, right? So if I decrease the number of reactants by the same relationship, if we have a decrease in the reactant concentration, then we're going to increase the Kc because they're inversely related, right? So we're going to increase Kc in this case. So this is correct. We would observe B as well. Now, let's think about an exothermic reaction now. So let me, where should I write this? Let's reset this, what I have down here, right? So let's reset this. If I have an exothermic reaction, it means that my delta H is negative. So the forward reaction is going to give off heat, right? So this is negative. So now let us change these here. Let's change this here so we're on the same page with this one. So now I have an exothermic reaction. Forward reaction gives off heat. So let me just write that here. When I go from A plus B to C plus D, it's going to give off heat because that's what exothermic reactions do. They give off heat, right? And then the reverse now is going to absorb heat, right? Absorbs heat. So let's take out this from here. Okay, so the forward reaction is going to give off heat because it's an exothermic reaction, and the backward reaction is going to absorb heat. Okay, all right. So if I increase the temperature, then what's going to happen is the equilibrium is going to shift in such a way that it can use up that heat that I'm putting in. It's not going to want to go to the right because that's going to cause it to give off more heat, right? So if I increase the temperature, it's going to want to shift in the direction where it absorbs heat. So it's going to want to favor the reactants. And so I'll actually have an increase in my reactants, which is not what they're showing here. So if I increase my temperature, I'm going to have an increase in my reactants, not a decrease. And if I have an increase in my reactants, then I'm going to have a decrease in my Kc. So this isn't right either. So this one is not correct. We would not observe this. Our answer here is C, okay? But let's check D as well. So if we have an exothermic reaction and we decrease the temperature, right? We have an exothermic reaction, so the forward reaction gives off heat, and I decrease the temperature of the system, then it's gonna want to go to the right to give off more heat to compensate for that drop of temperature that I did. It's gonna want to go to the right. And if it goes to the right, then we're gonna decrease the reactants, right? And favor more products. So if we decrease the reactants and we favor more products, then our Kc is gonna increase, and that's what they said here. So this last one is correct. We would see this, but what we wouldn't see is C, right? So and that's what they asked. They said, what observation would not be true? And that's C. Okay? So you just have to really make sure that you understand Le Chatelier's and that you understand what's going on in an exothermic reaction versus an endothermic reaction, okay?